So it's very nice they indicate that we should use slope to determine whether the points, and there's three of them listed there, are on the same line. Justify your conclusion algebraically. So if I was to look at those 3 points graphically, let's go ahead and plot them on the Cartesian coordinate plane. We're at 3, -5. So I'm sorry, 3, +5. So 3, 5 is one of our points. Another point that we have is -2, +6. So I'm going to go back 2 and up to 6. And then the final point that we have is -5, +7. -5. And then +7. So it's kind of close, but I don't think that they are collinear. If they were collinear, if I picked any 2 points, I should get the same slope. And I would compare both of them. But if you take a look at it, if I just kind of drew, that's terrible. Let me try that one more time. Let me draw this line. So I'm going to start here. It didn't like starting where I wanted it to start. But what I notice is, can I move that? No. There it is. What I'm noticing is that, if I look at the slope for the first 2, and then I look at the slope from the second to the third one there that are plotted, they have different slopes, so they're not collinear. Now, if I was gonna, well, I can see this slope is down 1/3, so this has a slope of -1/3. This other one has a slope of down 1/1, 2, 3, 4, 5. So I have a slope of -1/5 and a slope of -1/3. Now, certainly, if they were on the same line, they would have to have the same slope. They couldn't have different slopes, and that's not the case here. Now, it does say justify your conclusion algebraically. I suppose what I could do is I could find the equation of the line that goes through 2 of the points, and then I could test and see whether or not this third point satisfies that equation, if it makes it true. I already have a very strong sense that no, that third point will not, and I can see why from this graph. But the reason why I would take this a step further is this is just phenomenal practice, right? So the equation of any line can be written in the form y equals mx plus b. Of course, m is my slope, which is how the y values change divided by how the x values change, and this b value here is my y-intercept. Now, this is something that we've done, I think, since chapter 2 or 3. I mean, we've been doing this a lot, so it should be a relatively easy task for us. So let's look at the slope, change in y. Each one of our points, they have an x and a y, an x and a y. So in order to calculate the change in my y values, I'm going to take this 6 and I'm going to subtract 5. So in my numerator, I'm going to write 6 minus 5, and notice the order that I did that in. I'm going to do the same thing with the x's. I'm going to take this -2 and I'm going to subtract from that 3. So I'll write -2 minus 3. So I, in each case, was going from point B to point A. And it's important that you preserve the order that you're doing that subtraction. If you flip it, you're going to get the wrong sign of your slope. You'll get, if the slope is +3, you'll get a -3 instead if you do inadvertently flip one of those. My numerator here has a value of 1, and my denominator has a value of -5. And I realize now that I'm doing A and B, which is actually this line right here. So what I'm going to do is I'm finding the equation of this line, and then I'll plug this point in. Because I forget this was point A, this was point B, and this is C. So I'm finding the equation of this line and then verifying that point C is not on it. Point C is somewhere above it. So I do have the slope of -1/5, which is reassuring because when I look at this graphically, you can see it was here already, but I'm going down 1 and then I'm going over 5 units. So this does indeed have a slope of negative 1/5. I need to find the y-intercept now, and to do that, the technique we've customarily used is we would plug in a point and the slope and use that to calculate b. So I'm thinking this equation again, y equals mx plus b, and I'm going to use my first point, point A. Point A had a y value of 5, so I'm going to write 5 where y is. I had a slope of negative 1/5, and x had a value of 3, and then I'll write the plus b. So this is interesting. 5 is equal to negative 3/5 plus b. So on each side I'm going to add 3/5. So 5 plus 3/5 would be b. If I want to, I'll get a common denominator here of 5, so I'll rewrite the number 5 as 25/5. Right, that's what 5 is equal to, and then plus 3/5. So now you can see, now that I'm talking about fifths, I can combine those as 28/5, and then that is what b is. So I know my slope and I know my y-intercept. Slope was negative 1/5, y-intercept was 28/5. So the equation of this line is y equals negative 1/5 x and then plus 28/5. So our central question now is, does this point C satisfy this equation, right? Does that point make this a true statement? If it does, then they are collinear, right? If it does not, they're not on the same line. So when I plug in x is negative 5, I get, on this side I have a negative 1/5 times a negative 5 plus 28/5, which would make, this will just become a plus 1. So 1 and then plus 28/5. Of course, the number 1 can be written as 5/5 plus 28/5. And if I combine the 5 and the 28, that's 33. So I end up getting 33/5 on the right hand side. The question is that the same as y? And the answer is no. Y is 7, right? Now it's not far, right? If you look at it, it's close. I think 35/5 would be 7. This is just a little bit smaller than that. So the y value that I need is sitting above it. And I can see that, if I come back and look at the graph, again, we were finding, not this line, but we were finding the equation of this line. And notice that the value of c here, which was 7, is slightly above the c value that this equation had. So they are not collinear. They are not on the same line. And actually, they don't even use the word collinear, but that's what that means. On the same line means collinear. So in case you're wondering why I'm using that word, it's because the points would be collinear if they had identical slopes. If I picked 2 and then the other 2, and they had the same slopes, they would have to be collinear. They're not here.